How's everybody? Good? You're what? Out of quarantine. Oh, the sun has never looked so bright. Yeah, great. How many of you have been in quarantine already this semester? So, a couple, 3, 4, great. Well, glad to have you. Who'd like to start us off with a prayer? Thank you. Here.
Dear Heavenly Father, we're grateful for this beautiful day we have together in person and to learn more. And we ask that the Spirit can be here and help us remember the things that we do learn. And we're grateful for Brother Corey and his preparation, and yes, to bless him, and that we can also all remain healthy so that we can continue to come to campus and to learn from one another. We're grateful for the gospel, and we're grateful for the opportunity we have to be at BYU, and we love thee so very much. We say these things in the name of Jesus Christ. Amen.
First thing, let's look at homework over here. So you'll have 3.2 and 3.3a written, and then preparing for the second half of 3.3. I don't know how much we'll get to within verses today. So watch the 3.3b video, read the remainder of 3.3, and then do the 3.3b rub assign. So that will be in preparation for Thursday. Next Tuesday in a week, all we are doing is reviewing for the exam. So I should put on here also. Oh, that's not very dark. I didn't bring my big marker over. Oh, that's even worse. So start reviewing. Oops. And studying for the exam. Horrible markers. Okay. So there are 2 exams online, practice exams, so you can get on and do that. And for $50, I'll give you a sneak peek to the. No, I'm just kidding. I'm just kidding. You don't get to see the actual one. Yes. So they're the 7th, 8th, and 9th. Is that right, Michelle? I think I emailed out because someone asked, said we have dates in different places. So Gradescope, it will be on Gradescope, so you will do it online wherever you want within reason. I'm still trying to figure out some of the logistics. I've never held an exam through Gradescope. I'm trying to work with some of the professors who've already done it that way.
Your algebra.
Figure out. Yeah, I'll let you know. Figure it out. Yes. That's one of the things I'm trying to figure out. So, yeah, I'll let you know. Good questions. Sorry, I don't have the answer right now. Any questions about the forum or any comments about the forum? I got 2 thumbs up here. So, anyone want to share 1 or 2 interesting things? What was that?
I'm just a big fan of American history, so I'd like you to start.
Oh, right. That was interesting that on Thomas Jefferson's gravestone, it has 3 of his biggest accomplishments, and none of them are that he was a president of the United States. So, yeah. So, yeah, interesting. The ladies, I wrote down her name. I can't remember it. Melody Barnes. She did talk about religion and science, and you have to choose one over the other, faith and learning, and she emphasized you don't, and shared some things from a well-known biologist who lives in both. We should be very comfortable with that. Interestingly, for most religions, the more educated you become, the less likely you are to be faithful in that religion. It's the opposite as members of the Church of Jesus Christ of Latter-day Saints. The more educated, actually the more faithful and committed you are. So that it is interesting. I mean, yeah, from our doctrinal perspective, we believe in all truth, and science is part of truth, but also truth we receive through revelation is also truth. So, okay. So I'm just going to pull up a few slides. In 3.2, and there's a few theorems like this, where they just give a bunch of rules. Okay. Most of them are pretty straightforward. They either follow rules you'd expect from algebra that we know from the real numbers, or vector algebra that we've worked with. So addition of matrices is commutative, it's associative. You add the zero matrix to a vector to a matrix, it doesn't do anything. You add a matrix to the opposite of itself, you get the zero matrix. All of the entries add to zero. And then stuff you'd expect to have work with the scalars. So not a lot of surprises here with algebraic properties of matrix addition and scalar multiplication. Any questions on this? Okay. I know having questions on them versus knowing when to use them in the problem, I know those are two different things. So we will attack a bigger problem later today. And then properties of matrix multiplication. The big one that isn't here, of course, is AB does not equal BA, right? It's not commutative. Yes? Yep. Yep, you can. So if you have like a 4A plus a 3A, right? That is a 7A. Or if you have a 4A plus a 3A equals, oops, I meant to do equals on this, like equals minus a B, something like this. Yeah, then you can subtract 3A using these rules. You can subtract 3A from both sides. You'll end up with A equals a minus B. So yes, you can do that. Because of the rules with the scalar addition and the associativity and such that we just were looking at, you can do that to both sides. So, okay, good question. Any other questions? That was great. Okay, matrix multiplication. If you have three matrices multiplied together, we're assuming that the sizes work, so you can actually multiply them. It doesn't matter which order you multiply them. You can do well, be careful with order. You can't multiply A times C, right? But you can either do B and C first, or you can do A and B first. That one doesn't matter. A key thing when you're distributing or when you're solving equations is, because it's not commutative, you have to keep the multiples on the right side. So if you have A times the quantity B plus C, when you distribute that in, you have to be careful. You have to be careful that you write that as AB plus AC, where A is still on the left of both of these. And if we're solving an equation, AX equals B, when we get to solving with inverses, we would multiply A inverse on this side to cancel this out. We have to multiply A inverse by that on the left side. Do it on the left side for both. Okay? So things to watch out for. Scalars you can move around in pretty much wherever you want. Questions on matrix multiplication? Yes. That's right, of size M, because you could have A might be, this might be A. So what size would you multiply over here to get A out? Well, if you do this side, you're going to need a, let's see, do. I don't know if I'm going to do this right on the spot. You've got to have this, right? So there. So this will get you what you need. So you need, for a 3 by 2, you need to have a 3 by 3 on this side. But if you multiply, if you had A times something on this side, can you pull up the camera so people online can see me, please? So if we have this, and we're going to multiply something on this side, how big do we multiply it by to get A back? This is going to end up being a 2 by 2 identity matrix. 1, 2, here, you get the 1. 1, 2, second column, you get the 2, etc. So that's what they're emphasizing with that last one. You can always multiply a matrix by an identity matrix to get itself back, except if it's not a square matrix, you have to be careful with the sizes. You'll have different sizes on different sizes, different sides. Yes?
I may have thought of the answer while I was raising my hand, but there was a problem on the other side of my where it was like I like subscript 2 minus the number. And I was wondering what the subscript like the 2 was.
Oh, it just means it's a 2 by 2 identity matrix.
Like,
So
it came to my mind, but
yeah.
didn't teach us that before?
Yeah, because the identity matrix is always a square matrix, so they just have to specify one number.
I
So
just
that's
assumed it was a 2, otherwise I couldn't do subtraction.
right.
So why does it need to jump?
So it may be they were just helping you. Maybe you didn't need help.
By
But,
helping me, they confused.
okay, so let's go back to. Oh, Michael, you had a question? Okay. And properties of the transpose. So this is something we haven't dealt with with working with real numbers. So most of these are, again, straightforward. You take the transpose of the transpose, you get the matrix back again. A plus B, if you add two vectors to two matrices together and then you take the transpose, that's the same as transposing them first and then adding them together. Since K times a matrix is just K times all of the entries of the matrix, you can multiply that first and transpose it, or you can transpose it first and then multiply that in. Doesn't make a difference. This is the big one, okay? Let's spend some time talking about D. So I'm going to do this with two matrices. I'm going to call them 1, 2, 3, 4, and A, B, C, D. So we can keep track of everything. I don't want to do all numbers and I don't want to do all letters. And we will call this A, and we will call this B. And what we're interested in is AB transpose. Okay, so what does that equal? So let's calculate the product AB first, and then we'll transpose that. So it's going to be some 2 by 2 matrix, and then we'll have to transpose that. So we have a 1, 2 times an AC. So 1A plus 2C. When you have a 1, 2 times a BD, so 1B plus 2D. Then you have 3, 4 times AC, so that's 3A plus 4C. And then we have 3, 4 BD, 3B plus 4D. We still need to take the transpose of that. Okay. Then if I take the transpose, these diagonal entries will stay the same. 1A plus 2C, that'll be the same. 3B plus 4D. And here I have 1B plus 2D is going to be down here. 1B plus 2D. And up here I have 3A plus 4C. Now, if I want to factor down this matrix into two 2x2 matrices, see if you can figure out what goes here and see if you can figure out what goes here so that I could multiply them together and get that. Okay? So work on that. Do a little thinking. Don't make me do all the work. Is anyone out there making progress? You just drawing caricatures of the professor and, shooting arrows through him or something. You're on your scratch paper. Shooting arrows came to mind because my son was drawing pictures of Samuel the Lamanite last night up on the wall with a bunch of arrows going at him, but not hitting him. Okay. I doubt I'm so lucky on your paper. All right. Someone have an idea? Could someone see how they could factor this down? Michael?
I kind of looked at what were common numbers and letters as far as rows and columns.
Yeah?
The first column is-
Wait, hold on.
So I was looking for commonalities between rows and columns with the letters and the numbers. For example, the first column has 1 and 2 as that's common, and the first row has A and C that are common. So I knew that one of the matrices had to be in rows, and because they're oriented with rows and columns, then the first row needs to have a 1 and a 2 and an A and a C. And I was just, I guess, looking to see the 1s and 2s would have to be in the first column of the second matrices, and the A's and C's would have to be the first row of the first matrices for that to work.
Okay, very nice. So let me see if I can capture what he said up here. We do have AC, AC. We also have the 1, 2, 1, 2. And if you think about what you're doing, when you do this multiplication, this top row here ends up being in that multiple there ends up being in the top row in the final thing, right? So I'm going to go here to here, here to here. So what does that have to be? That has to be AC. Because I have an AC times here, which will get me this entry, an AC times here, which will get me this entry. And then here I have BD in the lower one. So BD here, that makes sense. That's what I have to have. So we get BD, BD. Okay? And then what has to be over here? Well, I have an AC times a 1, 2. That goes up here. The lower entry here, BD times a 1, 2, gets me that. So here I have 1, 2, and 3, 4. Does that make sense? BD times 3, 4 gets me my 3B plus 4D. Okay, so you might have been able to reason through it that way. I'd hope you could. Maybe I didn't give you enough time, but I'm confident if you thought about it some more, you could figure it out. And so what is this? How does that compare to what we started with? Yeah, A, first it's on the right, no longer the left, and it's not A anymore, it's A transpose. And B is on the left instead of the right, and it's no longer B, it's B transpose. Okay, so there's our proof that for a 2x2 matrix, there's a proof for a 2x2 matrix that for 2x2 matrices, A times B transpose is the same as B transpose A transpose. Okay, so yeah, it ends up, those products will end up being the same in here. Nope. In fact, they don't even have to be square. So you could have, let's check this way. So this transpose, I only end up with a number. That's not a very good example, but no, they don't even have to be square. So we got other things to talk about. We're not going to spend a lot of time doing that. So, yes.
So if it was like three matrices, if it was like ABC, would be C transpose B transpose A transpose?
Oh, so that's a good question about what about A, B, C transpose? Yeah, so you could break it down and think, okay, I'm going to think of it as A times B times C, and then we could apply this rule once, so it would be C transpose, and then times A B transpose, right? And then you can apply the rule again to get C transpose B transpose A transpose. Okay, yes. Right, because that's what we found out makes sense here. If we have AB transpose, this whole thing is AB transpose right here. It ends up being B transpose A transpose. So that switching the order is very important. So it was up on the screen and we took it off so people could see it. So yeah, that's what we were focusing on, is how to make sense of this. And to distribute that transpose, if you think of distributing the transpose, you have to reverse the order too. Okay? So this is a great example of, there's two kinds of proofs that we do in linear algebra. We actually don't have you guys do lots of proofs. When I took this class, it was very proof intensive. A lot of other places you'll take it, it's extremely proof intensive. But this is one kind of proof. These kind of proof, we actually done both kinds of proofs here. This kind of proof, you just keep with, you just use the rules and you don't have to dive into the individual entries. So you just keep matrices A, B, and C, and maybe some constants and whatever. But sometimes you have to dive into individual entries. Okay. I think I'm trying to remember what the on your homework coming up. I think it says if A and B are both n by n and symmetric, show that A plus B is n by n and symmetric. Okay? This is a situation where just staying at this level isn't going to help you. It doesn't get you anything. Because all you have is A plus B. You start with an A, you start with the B, you're adding them together. This is a situation where you actually want to start out writing the individual entries. And I just did this for a 2x2, but that doesn't work for general. So what you want to start doing is writing out A like this. Like A11, A12, A13, dot, 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 A1n. And A21 and A231, dot, 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 AN1, A22, A32, A23, A33. That's usually about as far as I go, and then you can do 8 and 2, ANN, A2n, etc. So I can write down this represents an arbitrary n by n matrix. And then I can write down another one for B. So B11, B12, B13. So you can fill it out. And then I can start working with these. Dang it. So if I start adding these together, what's the entry going to be? If I do the addition, I will have A11 plus B11. That's going to be that first entry in the sum. And then A12 plus B12. And this is what you start working with, and then you can take show that it's symmetric or whatever. I actually should have done something different on this particular problem. It's n by n and symmetric. So I just wrote, this is for an arbitrary A. This isn't necessarily symmetric. What do I know if this is symmetric? Yeah, these are the same, and these are the same, and these are the same, and these are the same. So what I should have done is written that out that way. I meant to. That's how it is in my notes. So I could just write this as 1, 2, 1, 3, 1n to show that these and these they're the same. And then when you add them up over here, you'll have A 1, 2 plus B 1, 2. So those are the same, right? And then you can argue, hey, this is symmetric too, because you can show that when you take the transpose, these opposite values are the same. So, okay. Just wanted to give you some help about these two different kinds. Sometimes I liked going here. I was very comfortable. I knew how to do this really well because you basically just get down and you're just working with regular numbers that you've been working with for a while. They were sometimes a little harder for me, but if you can do this, it's a lot slicker, a lot less work. It's just not all of them you can do that way. Okay. Okay, we're going to talk about the mathematics of regression. We bumped into this a little bit earlier, but I want to do it so we're a little bit more clear on what it is, and we're going to end up getting to an equation that we really want to solve. Okay? So you're used to things like this, right? Statisticians, they write it differently. They write it like this, okay? Or B0 and B1 are the coefficients. This generalizes a little more because you can call that x1, b2, x2, b3, x3, where this is, you can have as many inputs as you want, okay? Different variables. Now let's work with this. In our particular example, we are just going to work with one input variable and a constant. And the problem we're going to work with is predicting weight as a constant plus B1 times your height. Okay, or a person's height. I think these are males in the data set. So pretty simple linear regression. Well, as simple as you can get. It looks like we only have one input here, but when we do the math, we actually have to, or one vector here. When we do the math, we actually have to think about a vector here too. So in a data set, I would actually take the column of weights. So I'd have a weight 1, weight 2, weight 3. I can number all the people to n. In fact, I'll quickly pull this up and show. Okay, so like here, you've got weight and height. These are weights and heights for different people. But this B0 is actually multiplied by something. And it's a column of all ones. Okay, however many ones I need. N ones in a row. And that makes it so it's the constant, it's the same value for everyone in the data set. Okay, but this might be a little bit different than you've thought about it before. And then I have B1 times my height variable, my height values, N there. Okay, so I want to know what B0 and B1 are. Those are the coefficients. As soon as I know that, I'm done. Then I can just plug in someone's height, then I can get out their weight, or approximately their weight, right? Okay, and this we could write in a different way. I can rewrite B0 and B1 just as B as a vector, like a vector of unknowns. And mathematicians call these vectors, they call it X. It's your data matrix. So here, let me write it this way first. 1, 1, 1, 1, 1, dot, dot, H1, H2, down to Hn. okay, times b. And that whole thing will equal my w's. There's one mistake here, though. There's one mistake. Anyone know what it is? We're probably not equal. Only maybe if we had two people. But this is only about. Okay, we're approximating here. Because here I have two vectors. And here I have like the span of two vectors, right? This will span a plane as long as these are independent. So as long as h's are not all the same, then they're independent. Okay. And so here I have some plane. I have two vectors in that plane. Okay. For any b naught or b1, I can find b naught and b1 that gets me anywhere in this plane. But chances are this list, this vector is not in that plane. Could be, but because is everyone of exactly the same height, exactly the same weight? No. So it's not going to be in there. We're going to have another vector. This is our y vector. This is our outcome. And what we're trying to find is the projection of this vector down to this plane. Okay? We've learned how to do projections of a vector onto a vector. Now this is a projection of a vector onto some subspace. And we're running a little out of time, but anywhere in this plane, any vector in this plane can be represented as this matrix times b naught b1. We're going to just call this b. We're just going to call this as the x data matrix. So any point in here is xb. So any vector here is an xb. So this is some vec xb. I don't know what it is, but I want to figure out what the b is such that this xb and this projection here, this vector here, I want those to be orthogonal. Because the closest point I can get to from this point down to this plane is a perpendicular projection, right? It's an orthogonal projection. And this vector is y minus xb. For some b, we're trying to figure out that b. Is it y minus xb or is it xb minus y? It depends on which arrow. You can't see very well, but if this is y and this is xb, what's y minus xb and what's xb minus y? What's the difference? One point's one way, one point's the other way. Okay? An easy way to think about this is you always subtract your tail. So y minus xb, the tail of my vector is on xb. So y minus xb is doing that. xb minus y is doing that. But when I was on the test and I couldn't remember what it was, I would think about it as an addition problem. And here I would, so if I called this vector c, and I was trying to figure out which of these was c, I'd have y minus xb equals c. Well, that means y equals c plus xb. Which two vectors, which c, can I add to xb to get me y? Is it this one or is it this one? Right, the vector from here I have c can go up or c can go down. So my question is, can I add, if I add c, do I add this c or do I add this c? Like, which one of those is going to help me get to y? This one. So I know that this one has to be y minus xb. So I always had to reason about it that way because I couldn't keep them straight. All right, well, what does this mean? Using what we know about dot products, we can set up an equation that will allow us to solve for xb. Okay, that will allow us to solve for b, solve for our coefficients. So What is that equation? Well, what do we know about dot products of orthogonal vectors? So we know that xb, some xb, we want to find the beta that I can multiply by x, and then I can take the dot product with y minus x times that beta, and so the dot product is 0. Okay, your job, solve for b. Use what you know about matrix algebra and vector algebra and solve for b. Okay, I'm going to give you a few minutes. One thing to notice, first hint, this is a dot product, but these are matrix products. Okay, so think about it for a second. See what you can come up with. I want b equals something. And you're free to talk to your neighbor. You guys can work on this in pairs. Has anyone got any breakthroughs yet?
Oh, it's dot product is distributive, right?
Yep. Dot product is distributive. You can distribute. Anyone find a way to get away from the dot product? Who has their notes? Yeah, how can we, last time we talked about how to write a dot product as a matrix product. What did we do? Do you remember? You don't? What did we do? We used the transpose, right? So if we have 1, 2, 3, dot, 4, 5, 6, this is fine, but this is a dot product. How do we write this as a matrix product? What do we have to do? This has to be this way. So, okay. So if this was U and this was V, with the dot product, we can just do U dot V. But for a matrix product, it would be U transpose V. So So you can distribute this, or at the beginning, you can write XB transpose times Y minus XB equals 0. And now you don't have any dot products. All of these are matrix products. That might help. Okay. So go ahead and see what else you can come up with that. You can think about what you would do if you start thinking about them as numbers. How would you just solve B in a regular equation? It doesn't always work, but it can give you, might start pointing you in a good direction. Can get you in trouble, of course, because matrices don't always work that way, but. Okay, so I just distributed. So some of you are already distributing. So. Doesn't look like we're getting anywhere, does it? I just added it to both sides. What if so we learned something about distributing the transpose, how we can rewrite the transpose of a product, right? So that's B transpose times X transpose Y. And then this is B transpose X transpose X B. So at least for there. What are we trying to do again? Solve for B. So far, this is the easy part. There's just the hard parts right now. Can you divide by B transpose? Oh, so like, can we? It'd be nice to, yeah. If we could do something to this side of both sides to get rid of this. Okay. If B transpose was an invertible matrix, then we could. Okay. So we haven't talked about matrices. We haven't talked about inverse. I mean, you guys have just started reading about inverses. But if this product was invertible, this multiplication here was invertible, meaning I could undo it, I'd know how to exactly undo it, then yeah, we could multiply by the inverse. But what's the shape of B transpose? What's B? B is a 2 by 1. So B transpose is a 1 by 2. Does a 1 by 2 have an inverse? Only square matrices can have an inverse. Only square matrices can have an inverse. But nice thought. That's exactly the kind of thing you want to be thinking about. Like, hey, it looks like maybe I can cancel something out. But with matrices, well, we can only do the canceling if we have an invertible product. Yes? That's right. Very nice. Yes? Ah, so that's something else. You're like, hey, I've got this on both sides. Yeah, so great thinking. So what size would this be? That could be the first thing we could check. Let's see if it's even a square matrix, right? And so here we have a 2x1, I mean a 1x2 with a 2x, am I doing this right? Oh, this is a transpose. So I'm going to have a really long data matrix here, 1, 1, 1, 1, 1, height 1, height 2, height dot, dot, dot to hn. So I can do this product, but it ends up being a 1 by n. So that doesn't. By good thinking, right? We're running out of time. I'll give you one more, or one other way to think about this is we have B transpose times this, we have B transpose times this. So maybe we can equate those. Maybe those have to be the same. They don't have to be the same, but if they were the same, then it would be one solution. Right? So I have the B transpose, I have the B transpose, and then these sides could be the same. Oh, right. So you say, what about this and this? Yeah, so there's two ways to look at that. This one turns out to only, this is a solution, but Y has to be inside the span. And we already know there's not a B naught and a B1 that'll get us that. So yeah, so that's actually a nice way to see that. It is one solution if it's inside. This other one provides us a solution even if it's not inside. So X transpose Y, if that equals X transpose X B, then we have a solution. How can we solve for B now? It's the strategy that I've shot down twice already in class. An inverse. If X transpose X has an inverse, then we could multiply both sides by X transpose X inverse. Because X transpose X inverse times X transpose X, and it turns out as long as the columns of X are linearly independent, X transpose X will be an invertible matrix. It'll have columns that are independent. So B, yes, it turns out to be a symmetric matrix. For those of you going to statistics, this is called a covariation matrix. The X transpose X is your covariation matrix. But this simplifies to just the identity times B. And this tells us exactly what we need to do with our data matrix and our output to actually calculate our coefficients. This we've just derived. These are called the normal equations. They're called normal equations because you can derive them through this normal projection. I was going to pull it up, but if you go to Wikipedia and type in normal equations, it'll show you that exact thing. So we can actually do this here. Here I've got my weight as my outcome and my constant times my height. That's my X, those are my X coordinates, or my X matrix there. And we could calculate everything we need to on that left-hand side. So what's X transpose times X? So X transpose times X. Did you guys know you can do matrix multiplication in Excel? M mult. So MMULT does matrix multiplication. So you do one array. So I want this array. Oh, there's only 253. Okay. I can type it in for the rest now. 253, but I need X transpose, not X, right? So there's a transpose function. I just type transpose. So I'm going to transpose that. And then I'm going to multiply it by C2 D253. So the matrix multiplication is you put your two your two matrices in there, you hit enter. Oh, dang it. Yeah, what did I make? 253, 253. It looks like it. Maybe I need x times x transpose. No, I should have x.
Yes, it will be.
I shouldn't need it, but I can try it. Oh, man. I did this before class. It really works. I'll have to do it later. Well, I was going to show you that we get the same thing as if we just do the regression in Excel, but what a letdown. All right, have a great day, you guys. So this is supposed to illustrate the power of matrix algebra, where you can derive these equations like this that give you straightforward results, and you don't have to do calculus. So. Ugh. Michelle, you're throwing me off. Okay. Where did I put my blue pen?